Good morning, I am Seema from BSc Chemistry Honors second year. This video is usually for the visually impaired students. Thermodynamics. Introduction for the second law and different statements of the law. The first law of the thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law as a consequence, some definitions given to the second law are briefly given below. A major limitations of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of the energies involved, but it provides no information concerning the feasibility of the process, that is, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold hand to a hot end or not. All that it tells is that if this possible occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies the answers to above questions by stating that all spontaneous processes like the flow of the heat from the hot end to cold end, diffusion of the gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. The term spontaneous process used in the above definitions means a process which can take place without the help of any external agencies. All natural processes, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that the term spontaneous does not give any idea of the rate of the process, that is, whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of external agencies. The first law states that when heat is converted into the work obtained is equivalent to the heat absorbed. However, it has been seen from the experience that the heat absorbed cannot be completely converted into the work without leaving some changes in the system of the surrounding. For example, the heat absorbed cannot be completely converted into the work without leaving some change in the system or the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as follows. The complete conversion of the heat into the work is impossible without leaving some effects elsewhere. This is the second definition. Besides the above definitions, a number of the other definitions have also been given to the second law of thermodynamics. The two important ones are: it is impossible to construct a machine functioning in the cycles which can convert the heat completely into the equivalent amount of work without processing some changes elsewhere. Without the use of an external agencies, heat cannot be produced. It is impossible to construct a machine functioning in cycles which can convert the heat completely into the equivalent amount of the work without processing some changes elsewhere. Without the use of an external agencies, heat cannot by itself pass from a colder to a hotter region. The term functioning in the cycles is introduced in the above definitions to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is equal to 0, so that Q is equal to W, that is, the work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into the work. However, it is important to observe that this conversion is accompanied by an increase in the volume of the gas so that the system has undergone a change. A number of the other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding the section of this chapter. The fraction of the heat absorbed by a machine that it can transform into the work is called as the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by neta is equal to W upon Q. The machine used for the conversion of the heat into the work is called heat engine. In order to bring about this conversion, the heat absorbs heat from a heat reservoir at a higher temperature called the source converters a part of it into the work and returns the remainder to heat reservoir at a lower temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sardin Carnot devised a technique called the Carnot cycle. A cycle is a process in which a system returns to its original state after a number of the successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot, called the Carnot engine for the purpose of calculation of the efficiency, was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with the weightless, frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason, it is also called the reversible heat engine. The cylinder is supposed to be insulated on all the sides except at the bottom so that the heat can flow or to or from the system only through the bottom. Further, it is supposed that there are two reservoirs, one at the higher temperature T2 called the source and the other at the lower temperature called the sink, and if some operations is carried out by the places the cylinder in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an isolating material, no heat exchange can take place between the system and surroundings and hence the process is adiabatic. The Carnot cycle consists of 4 different operations which can be represented on a pressure volume diagram, sometimes called the indicator diagram. These operations are carried out as shown, are briefly described. First is the isothermal expansion. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source heat reservoir at a temperature T2. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Says the gas is the ideal. The work done W1 by the 1 mole of the ideal gas will be given by minus W1 is equal to RT2 ln V2 upon V1. Further, for a ideal gas, the work done is equal to the heat absorbed Q2, so that minus W1 is equal to Q2 is equal to RT2 ln V2 by V1. Adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes the V3. The path is shown by the adiabatic curve BC. The work W2 will be given by minus W2 is equal to CV T1 minus T2 minus CV into T2 minus T1, where CV is the heat capacity of the ideal gas. Here again W2 is negative by the usual convention of sign. Third, isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink, the heat reservoir at the lower temperature T1. The gas is compressed isothermally and reversibly till the volume decreases from the V3 to. The process is represented by the path CD. The work done is taken as the positive by the usual convention of the sign and hence will be the given by W2 is equal to RT1 ln V1 4 pi upon V3. During the operation, an amount of heat Q1 exactly equal to W2 will be returned to the sink at T1. Heat has been given out by the system using the appropriate convention of the sign. Q1 will be negative and W2 will be positive, so that minus Q1 is equal to W2 is equal to RT1 ln V4 upon V3. Adiabatic compression. The cylinder is now removed from the sink and placed against on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state of A is regained. The temperature of the gas rises from the T1 to T2. The work done is positive by the conventions of the sign and will be given by W4 is equal to CVT2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been completed. The net work done by the system will be given by W is equal to minus W1 plus minus W2 plus W3 plus W4. RT2 ln V2 upon V1 minus CVT2 minus T1 into plus RT1 ln V4 by V3 plus CVT2 minus T1. RT2 ln V2 upon V1 plus RT1 ln V4 upon V3. Since V1 and V4 lie on adiabatic curve and V3 V2 lie on another, it follows that V4 upon V1 raised to the power gamma minus 1 is equal to T2 minus T1. V3 upon V2 whole twice is gamma minus 1 is equal to T2 upon T1. Comparing the equation 9 and 10, we get a relation is V4 upon V1 is equal to V3 upon V2 and V4 upon V3 is equal to V1 upon V2. Putting these values in this equation, that we can get RT2 ln V2 upon V1 plus RT1 ln V1 upon V2 is equal to RT2 ln V2 upon V1 minus RT1 ln V2 upon V1. RT2 minus T1 ln V2 upon V2. Dividing 12th and 2 equations, we get a relation that W upon Q2 is equal to T2 minus T1 into T2, which gives the efficiency of the Carnot cycle or the engine. What is Carnot theorem? From equation, we can clearly saw that the efficiency of the reversible heat engine depends upon the temperature of the source and the sink, and it is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operations, because the work done in the adiabatic operations cancels the one another. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum, whereas the work done on a gas during the reversible isothermal compression from C to D is minimum. Hence, the total work done by the system, that is reversible heat engine or Carnot engine, is maximum for the specified conditions, and therefore the efficiency is maximum. The result that follows from the Carnot cycle as derived and discussed is called Carnot theorem. It may be the efficiency of a reversible heat engine depends only upon the temperature of the source and the sink, and is independent of the nature of the working substance. In other words, all reversible heat engines working between the same two temperatures have same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for a given temperature, since the quantity T2 minus T1 upon T2 is always less than the unity. The efficiency of the heat engine is thus always less than the unity. In view of our discussion, the second law of the thermodynamics is sometimes defined as follows. A heat engine absorbs a certain amount of the heat from the source, converts a part of it into the work, and returns the rest to the sink. In other words, it is impossible to convert the heat completely into the work. Combining equations 2nd, 5th and 8th, we get a relation that W is equal to Q minus Q2, Q2 minus Q1. That is, the net work done by the system is equal to the net heat absorbed by the system. Putting the value of W in equation 13, we get Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. Hence, the efficiency of a heat engine may be given by any one of the following expression. Nita is equal to W upon Q2 is equal to Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. This results derived for a reversible Carnot cycle leads to the introduction of a new thermodynamic term called the entropy, as discussed. The next topic is thermodynamic scale of the temperature. From our earlier studies, we are familiar that a thermometer is constructed most commonly by taking the suitable amount of mercury in a glass bulb at the end of a capillary tube and marking 0 when it is placed in contact with the ice and marking the 100 when it is placed in the boiling water. The length between the 2 points is then divided into the 100 equal parts. called the degrees. The scale of the temperature thus obtained is called Celsius scale of temperature. However, because different liquids expand to different extents, their coefficients of the expansion are different and also they do not expand the uniformly over a given range. Thermometers constructed by using the different liquids, we will show different numerical values of the temperature between their fixed point. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by the study the properties of the gases. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degrees absolute. The scale developed on this basis is called perfect gas temperature scale and is found to independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken in the heat engine. This scale of the temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly described below. Suppose there are two constant temperature heat reservoirs, one acting as a source and the other is a sink, and a reversible heat engine operates between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of the heat absorbed from the source and the heat lost to the sink. If Q2 is the heat transfer from the source heat reservoir at a higher temperature and Q1 is the heat transfer in the sink reservoir at a lower temperature, then if their temperatures on the thermodynamic or the Kelvin scale are represented by theta 2 and theta 1 respectively, we shall have Q2 upon Q2 is equal to theta 2 upon theta 1. Thus, this ratio of two temperatures has been defined in a manner independent of the nature of the thermometric substances, taking the reciprocals of the both the sides of equation first and subtracting these results from the unity. 1 minus Q1 upon Q2 is equal to 1 minus theta 1 upon theta 2. Q2 minus Q1 upon Q2 is equal to theta 2 minus theta 1 upon theta 2. Putting theta 1 is equal to 0, that is 0 of the new scale, we get Q2 minus Q1 upon Q2 is equal to 1. This implies that the 0 on the Kelvin scale is the temperature of the sink for a reversible heat engine whose efficiency is unity, that is, which is capable of converting the heat completely into the work. But from equation 14, page 86, it may be seen that it possible only at absolute zero on the ideal gas scale of the temperature. This leads to the conclusion that the Kelvin scale and the gas scale are the identical provided the gas is ideal. The temperatures on the thermodynamic scale are therefore expressed in the terms of the degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equal to that of the triple point of the water which is 273.16 Kelvin, then Kelvin is exactly equal to the Celsius degree. For this reason, the temperature on the absolute scale in the melting point of the ice is taken as 273.16 degree is often referred to as degree Kelvin. It may be concluded that thermodynamic scale of the temperature as defined on the basis of the second law of thermodynamics is more basic than that based on the ideal gas because of the any fluid can be used. However, the ideal gas scale is more practical for the laboratory use. Concept of entropy, entropy as a state function. For a reversible Carnot cycle working between the temperatures T2 and T1, it has been said that Q2 minus Q1 upon Q2 is equal to T2 minus T1 into T2, where Q2 is the heat absorbed isothermally and reversibly at the temperature T2, and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simplified as 1 minus Q1 upon Q2 is equal to 1 minus T1 upon T2, or Q2 upon T2 is equal to Q1 upon T1. Q upon T is equal to constant. Thus, we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation second, Q2 is the heat absorbed at a temperature T2 and Q1 is the heat lost at a temperature of the T1. If Q1 were the heat absorbed at temperature T1, equation second would be written as Q2 upon T2 is equal to minus Q1 upon T1, or Q2 upon T2 plus Q1 upon T1 is equal to 0. Now considered any reversible cycle ABA may be regarded as boiling made up of number of Carnots drawn across the diagram as shown this. Starting from the A and going through all the cycles successively from A to B, it can show all the paths inside the closed curve. APA cancels each other, leaving only the zigzag path, which is almost the same as path ABA of the reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of infinite number of Carnot cycles. For each of these cycles, we have sigma q by t is equal to 0, hence for an infinite number of the Carnot cycles, where delta q is very small quantity of the heat absorbed at temperature T during the small isothermal change of reversible process. Further, the above term may be divided into two parts, one of the path A to B and other for the back path B to A. Summations: sigma q upon t is equal to summation a to b del q upon t, summation b to a del q upon t is equal to 0, or may be written as summation a to b del q by t is equal to minus summation b to a del q by t. Q upon t is a to b and minus q by t is b to a. This implies that the total value of the quantity Q by T for the path A to B is equal to the total value of the quantity Q upon T for the reserved path B to A. Hence, it may be concluded that quantity Qt is a state function. Its value depends only upon the initial state A and final state B, and is independent of the path. Obviously, Q upon T is the change in the value of a quantity or a function having some definite values at A and B depending upon the values of pressure, volume, temperature. This quantity or function is called entropy and is usually represented by the symbol S. Thus, if SA is the value of entropy at A and SB is the value of at B, then we must have Q upon T is equal to SB minus SA is equal to delta S, where delta S represents the total change in the entropy in going from initial state A to final state B. Hence, entropy may be defined as the state function, the change in the value of which from the initial state to the final state is equal to the quantity Q upon T, that is total heat absorbed reversibly and isothermally in going from the initial state to the final state, divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of the heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that as the entropy is a state function, therefore the value of the entropy change during a process should not depend upon the path, that is, whether the heat is absorbed reversibly or irreversibly during this process. However, since the derivation of above result is based upon the Carnot cycle in which the heat is absorbed reversibly, Therefore, this expression for entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol Q reversibly in place of Q. The expression 6 may be written as delta S is equal to Q reversibly by T. Further, as entropy is a state function, a small change its value can be represented by ds. Hence, we may write as ds is equal to Q reversibly upon T. Units of entropy. From the expression delta S is equal to Q by T, it is obvious that units of entropy will be calories per degree. If heat is expressed in the calories, further entropy is an extensive property. It is therefore important to mention the quantity of the substance involved. It is usually expressed for the 1 mole of substance. Hence, the entropy units are calories per degree per mole. If heat is measured in the joules, the units of entropy will be joules per degree per mole. Is entropy change is in a reversible process. Suppose a process occurs under the completely reversible conditions, that is, the heat is absorbed by the system reversibly and the heat is lost by the surrounding also reversibly. If Q reversibly is the heat absorbed by the system reversibly, then the heat lost by the surrounding will also be Q reversibly. If the process takes place isothermally at the absolute temperature T, then entropy change of the system will be given by delta S system is equal to Q reversibly upon T. Entropy change of the surrounding will be given by delta S surrounding is equal to minus Q reversibly upon T. Hence, the total entropy change for the combined state and the surrounding will be the delta S system plus delta S surrounding is equal to Q reversibly upon T is minus Q reversibly upon T is equal to 0. Thus, we concluded that in a reversible process, the net change for the combined system and the surrounding is 0. There is no net change in the entropy. Entropy change in an irreversible process. If any part of the process is irreversible, the process is a whole is irreversible. Suppose that the total heat lost by the surrounding is Q reversible. This heat will be absorbed by the system, but the entropy change of the system does not depend upon the heat actually absorbed, but it depends on the heat absorbed reversibly, that is, on the quantity Q reversible. Thus, if the heat is absorbed the simultaneously isothermally by the system at the absolute temperature T, the entropy change of the system will be delta S system is equal to Q reversibly upon T. Further, suppose that the loss of the gas heat by the surrounding takes place infinitesimally slow, that is reversibly and isothermally at temperature T, then the entropy change of the surrounding will be the delta S surrounding is equal to minus Q irreversible upon T. The total entropy change for the combined system and surrounding will therefore be delta S system plus delta S surrounding is equal to Q reversibly upon T minus Q reversible upon T. Now we know that the work done in a reversible process is the maximum work. W reversible is greater than the W irreversible. Further, as the entropy energy is a state function, the value of the internal energy is same whether the process is carried out reversibly or irreversibly. Delta U is equal to Q reversible minus W reversible is equal to Q irreversible minus W irreversible. Combine the result fourth and fifth, we concluded that Q reversible is greater than the Q irreversible. Q reversible upon T is greater than Q irreversible upon T. Q reversible upon T minus Q irreversible upon T is greater than the 0. Combining these results with result given in equation third, we observe that delta S system plus delta S surrounding is greater than the 0. Thus, it may be concluded that in an irreversible process, the entropy change for the combined system and the surrounding is greater than 0. That is, an irreversible process is accompanied by a net increase of the entropy. Since all the spontaneous processes are thermodynamic irreversible, first definition of the second law of thermodynamics, it may be stated that all spontaneous processes are accompanied by a net increase of the entropy. This is also one of the very common statement of the second law of the thermodynamics. The results for the entropy change in a reversible process and that in a irreversible process may be combined together and put in the form of delta S system plus delta S surrounding is greater than or equal to 0, where the sign equal to stand for the reversible process and sign greater than for the irreversible process. The exact calculation of the total entropy change during an irreversible process, example when heat flows from a body B at higher temperature T2 to a body A at lower temperature T1, when brought in contact with it may be carried out as follows. Suppose the heat lost by the body B is represented as Q irreversible. The flow of heat may be allowed to make the place infinitely slow so that it absorbed by the body of A reversible and isothermally at T1, which may be represented as Q reversible. The entropy change of the body B will be also bend only a Q reversible. Hence, entropy change of body B is minus Q reversible upon T2. Entropy change of body A is equal to plus Q reversible upon T1. Minus sign indicates decrease in the entropy while positive sign indicates increase. Delta S total is equal to minus Q reversible upon T2 plus Q reversible upon T1 is equal to Q reversible into 1 upon T1 minus T2. The as discussed above for the reversible process, the result given in equation delta S system plus delta S surrounding is greater than 0. Delta S system is greater than delta S surrounding. Putting these values, then we get a relation ds system is greater than dq. This is the Clausius inequality. These equations show that irreversible processes are accompanied by increase in the entropy. This is further illustrated with the following two examples of the irreversible process. Spontaneous expansion, irreversible adiabatic expansion. Suppose the system undergoes the irreversible adiabatic change, then dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0. The entropy of the system has increased further as dq is equal to 0. This means that no heat is transferred into the surrounding. Thus, ds surrounding is equal to 0. Hence, total entropy change ds total is equal to ds system plus ds surrounding is equal to ds system. But ds system is greater than the 0. Hence, ds total is greater than the 0. Irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant, that is du is equal to 0. Hence, according to the first law of the thermodynamics, du is equal to dq plus dw, dq is equal to dw is equal to 0 or dq is equal to minus dw. If the gas expands freely into the vacuum, no work is done, so that dw is equal to 0. Substituting in seventh equation gives dq is equal to 0. Hence, by Clausius inequality, ds system is greater than the 0 further as dq is equal to 0. This implies that ds surrounding is equal to 0. Hence, the total change as in this case is ds total is greater than the 0. Spontaneous cooling. Suppose heat is transferred from one system at the higher temperature T2 called the source to the another system at lower temperature T1 called the sink. If heat Tq leaves the source and enters the sink, then entropy change of the source is minus dq upon d2. Entropy change of sink is plus dq upon t1. Total entropy change is dq by T1 minus dq upon T2 is equal to dq into 1 upon T1 minus 1 upon T2. As T2 is very greater than T1, ds total is equal to positive, that is cooling. Transfer of the heat from a hot body to a cold body is accompanied by the increase of the entropy change of the universe. Since all the spontaneous processes occurring in the nature are thermodynamically irreversible, these are accompanied by increase of the entropy. Hence, it may be concluded that the entropy of the universe is continuously increasing. This result is sometimes taken as another statement of the second law of thermodynamics. Thus, the main ideas for the first law and the second law of the thermodynamics may be summed up in the following statement: the energy of the universe is constant, whereas the entropy of the universe is continuously increasing and tends to maximum. Entropy change for the ideal gas with change in P, V, and delta T. Considered 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. If an infinitely small amount of the heat del Q reversible is applied to the system reversibly and isothermally at the temperature T, then the entropy change accompanies the following will be given by ds is equal to del Q reversible upon T. According to the first law of the thermodynamics for the infiniteness process, del Q is equal to du minus del W if the process is carried out reversibly. Equation second may be written as del Q reversible is equal to du minus del W. Further, if the work is restricted to the work of expansion, as is usually the case of the processing, considering in the chemical thermodynamics, then minus del W is equal to PdV, where dV is the small increase in the volume. P is the pressure of the system, which is very nearly equal to the external pressure because the process is carried out reversibly. Putting the value of del W from equation 4th in equation 3rd, we get del Q reversible is equal to du plus P dV. Substituting this value in equation 1st, we get ds is equal to du plus P dV upon T, or it may be written as Tds is equal to du plus Pdv. Now for 1 mole of an ideal gas, we know that Cv is equal to du by dt and du is equal to Cv dt, where Cv is the molar heat capacity at constant volume. Pv is equal to RT. From ideal gas equation, V is equal to RT upon V, where V is the volume of the system at the constant temperature and pressure and R is the gas constant. Putting this value du and P from equation 7th and at the we get a relation that dTs is equal to Cv dt plus RT upon V and dV. ds is equal to Cv dt upon T plus R dV upon V. If the volume changes from the V1 to V2 when the temperature changes from T1 to T2, then the entropy change accompanies the complete process will be given by integration of the S1 upon S2. ds is equal to integration of the T1 upon T2 Cv dt upon T plus integration of limits to V1 to V2 R dV upon V. Assuming that Cv remains constant in the temperature range T1 to T2, equation may be written as delta S is equal to Cv ln T2 upon T1 plus R ln V2 upon V1. This is an expression for the calculation of entropy change of the 1 mole of an ideal gas accompanies a process when temperature changes from the T1 to T2 and volume changes from V1 to V2. Further, for the 1 mole of ideal gas, we may write P1 V1 is equal to RT1 for ideal gas. P2 V2 is equal to RT2 for the final state. Dividing that, we get a relation that P2 V2 upon P1 V1 is equal to T2 upon T1. V2 upon V1 is equal to T2 V1 T1 upon P2. Putting these values in equation 11th, we get delta S is equal to Cv ln T2 upon T1 plus R ln T2 P1 upon T1 P2. Further, we know that Cp minus Cv is equal to R or Cv is equal to Cp minus R. Putting these values in equation 15th, we get delta S is equal to Cp minus R ln T2 upon T1 plus R ln T2 P1 T1 P2 Cp ln T2 upon T1 minus R ln T2 upon T1 plus R ln T2 upon T1 plus R ln P1 upon P2. Delta S is equal to Cp ln T2 upon T1 plus R ln P1 upon P2. This is the expression for the calculation of the entropy change of the 1 mole of the ideal gas accompanies a process when the temperature changes from T1 to T2 and the pressure changes from P1 to the P2. Entropy change of an ideal gas in different process Equation 11 gives the entropy change for the 1 mole of an ideal gas when temperature and volume are variables. Similarly, this gives the entropy change of 1 mole of the ideal gas when temperature and pressure are variables. These equations are modified if the conditions of the constant temperature, pressure or volume are imposed. For example, if the temperature is kept constant, that is T1 is equal to T2. Equation 11 and 16 are reduced to delta S is equal to RLN V2 upon V1 is equal to RLN P1 upon P2. Alternatively, this expression can be derived directly as delta S is equal to Q reversible upon T minus W maximum is equal to Q reversible is equal to nRT ln V2 upon V1 nRT ln P1 upon P2. Substituting the value of Q reversible from equation 19 and 20, we get that putting n is equal to 1 for 1 mole of ideal gas, we get the result given that if pressure is kept constant for isobaric process, that delta S is equal to Cp ln T2 upon T1. If volume is kept constant for isochoric process, then delta S is equal to Cv ln upon T2 upon T1. Note carefully that all the expressions derived above for the calculation of entropy change involve the natural logarithms. Since logarithm table commonly used are to base the 10, in applying these formulas, in x has to be first replaced by 2.303 log x, where x is the quantity like T2 upon T1, V2 upon V1, etc. Further note that if a gas expands irreversibly but adiabatically, then as for such a process Q reversible is equal to 0. Therefore, delta S is equal to 0. Entropy change during the physical change, a phase change. A change of the phase occurs in any one of the following cases: when the solid melts, or conversely when a liquid freezes, when a liquid evaporates, or conversely when a gas condenses, when one crystalline form the changes into the another, when the change of phase compensates, the temperature remains the constant till the change of the phase is completed. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called the latent heat. It is further termed as latent heat of the melting, latent heat of vaporization, etc., depending on the nature of the process involved. In the general, if delta Th is the latent heat and T is the temperature at which change of the phase occurs, entropy change accompanies the phase will be given by delta S is equal to delta IH upon T. The entropy change delta S is termed as entropy of the melting, entropy of the vaporization, depending upon the nature of the process. For example, we have the entropy of the melting or the fusion. Delta S T is equal to delta fusion H upon T fusion, where delta fusion H is the latent heat of fusion, that is melting, and Tf is the melting fusion temperature. Entropy of the vaporization delta SV is equal to delta vaporization H upon Tb. Delta vaporization S is the latent heat of vaporization and Tb is the boiling point. Temperature. It may be mentioned here that process like melting and evaporization involve the absorption of the heat, which is taken as positive by convention of the sign. Therefore, delta S for these processes is positive. That is, these processes are accompanied by increase of the entropy. On the other hand, the reversible process like freezing and condensation involve the evolution of the heat, which is taken as negative. Therefore, for this process delta S is negative. That is, these processes are accompanied by decrease of the entropy. It may be remembered as that if the heat is measured in the calories, the units of the entropy change are calories per degree per mole. If heat is measured in the joules, the units will be the joule per degree per mole. The next question arises that the physical significance of the entropy measure of the disorder. as an examination of the various processes which are accompanied by the net increase of the entropy shows that they are the associated with an increase the randomness of the distribution. For example, the melting of a solid is accompanied by a net increase of the entropy, and at the same time we know that the molecule atoms or ions in a solid have the fixed position and they have become free to move about in the molten state. This is expressed by saying that no disorder among the molecule, atom, or ions in the solid, but the disorder sets in when the solid changes to into the liquid. In the other words, it is stated that the randomness has increased. The vaporization of the liquid is accompanied by net increase of entropy, and at the same time the disorder of the randomness also increase because the molecule of the vapor and more randomness than the molecule in the liquid. Heating a magnetized iron needle demagnetize it because the molecule of magnetized iron needle which are oriented in a particular fashion lose the order on heating and become the disordered. Randomness increases all spontaneous process like diffusion of gases, flow of heat from the hot end to cold end of an iron bar are accompanied by a net increase of entropy as well as increase of randomness or disorder. For example, in the phenomena of diffusion, the two gases which are separated initially get mixed up in a random manner. Similarly, in the flow of the heat, the electron present on the hot end and having the higher kinetic energy rush to cold the end, thereby making the distribution more random. Hence, it may be concluded that entropy is a measure of randomness or disorder of system. This concept may be further understood with the help of following example. In a college, when all the classes are being held, all the students are sitting in the respective classrooms and disorder is minimum. As soon as bell goes, the students of different classes come out to go to the other rooms and thus get mixed up. In other words, disorder or randomness increases. In the game of the hockey or football, to start with, all the players take up some definite positions and thus are said to be in order. As soon as game starts, players start running and thus they are said to have increased the randomness with increase the further as the game catches more and more momentum. Thank you.